Okie dokie. Let's see if this thing really works today. We've got a brand new day, brand new setup, brand new everything as we're working through. Nothing's brand new. It's just been moved to another side of the room. But we're going to talk about optimization problems today. Optimization problems are also known as, aka, max-min problems. And the question of the day is, where do maximums and minimums occur? Excellent. Okay. And how do we find critical numbers? Nice. There you go. Okay, so that's what we have going for us as we move forward. Looking for maximums and minimums, which definitely, I don't have any of the other controls on here, so I'm going to have to go old school. Okay, so the maximum and minimum occur at the critical numbers. And that's when f primed of x equals 0. Okay, so let's move forward as we go on our merry way here. So a typical problem that we might look at is something like find the two positive integers such that the product is 350 and their sum is a minimum. So two positive integers such that, so we're just going to call them the two positive integers. One of them is going to be x and the other one's going to be y. Okay, so their product is 350 and their sum is a minimum. So we're going to, now how do we do with a product? Product means multiply. So x times y equals 350. And we want their sum to be a minimum. So for sum, we're going to use the letter s, and s is equal to x plus y. So this is the thing that we're going to try to minimize, the sum equation. And so this is the thing we're going to have to take the derivatives of. And so what we want to do is try to make it so we just have a nice simple derivative to deal with. So we're going to take this equation and solve it. Y equals 350 over x. Okay? So when we replace y equals y with 350 over x, this equation becomes x plus 350 over x. I don't think this should say integers. I think it should say numbers. Okay. So x plus 350 over x. That's the thing we're trying to minimize. So as we said, minimums and maximums occur at the when the first derivative is equal to 0. So we're going to do s primed, and s primed is, well, the derivative of x is 1. The derivative of 350 over x is I'm going to give you, I would say take the time to make sure that that's accurate, but it's negative 350 over x squared. Okay, my pen's acting a little weird because I'm in a different location, different computer, I don't know what. But so that's what we want to equal 0. So when is 1 minus 350 over x squared equal to 0? Well, that's when 350 over x squared is equal to 1, or when x squared is equal to 350, or when x is equal to the square root of 350, which is definitely not an integer, so that's why I said this should be numbers up here. X is equal to the square root of 350, and then y is equal to 350 divided by the square root of 350, which means that it's also the same. Okay, we want to check our answer with the second derivative test. So when we do the second derivative, s double primed, derivative of 1 is 1. This is going to become 700 over x cubed. Slow down, take a second to make sure that's accurate. And when x is equal to the square root of 350, it's going to be positive, right? Okay, if it's positive, that means we're opening upward. That means we have a minimum. Ta-da! There we go. So that's that first problem. Other sort of problem we look at, same sort of thing. Find two positive numbers such that the sum is 85 and the product is a maximum. So sum, we're talking about x plus y is equal to 85. And the thing we're trying to maximize is the product, and the product is x times y. So same strategy. We're going to solve for y. We're going to solve for y. I didn't think moving 8 feet across the room is making that big a difference, but apparently it is. So product x times 85 minus x, which we're going to simplify to 85x minus x squared. Okay, derivatize, take the derivative, because we know that max and mins occur at the critical numbers. Critical numbers happen when the derivative equals 0. P primed is 85 minus 2x. We make that equal to 0, so 85 minus 2x equals 0. 2x equals 85. X is 85 over 2, which is 42 and some change, 42.5. Okay, so if that's the case, so 85 minus half of 85 leaves me the y to be the other half of 85, and so we think we have answers. Let's check it with the second derivative test. So let's go over here and do p double primed. Ooh, derivative of this. So this is just going to be equal to negative 2. And when x is equal to 85 halves, is negative 2 positive or negative? Well, I think that's negative, right? And so that means we're opening downward, and that means we do indeed have the max that we're looking for. Okay, see how that works? So we're going to basically, for today at least, have equations sort of like this. They're going to add some slight conditions, things like the sum of the first plus twice the second. So you just have to set up this initial equation and go from there. Okay? Oh, here's my almost favorite problem in the whole world. A sandbox is to be constructed by cutting the corners from an 8 by 12 sheet of copper. What dimension should be cut in order to provide the maximum volume? Thank you for reading that aloud to us, Mr. Take. So we know that it's 8 foot this way, and we know that it's 12 foot this way. Okay? And so we want to figure out the maximum volume. Okay? So we're cutting out some distance from each corner. So we don't know what that is, so we're going to call it x. Okay, if we cut x from each side here, what's this inner dimension right here? That's right, it's 8 minus 2x. And what's the long way dimension? The long way dimension is 12 minus 2x. So if I'm doing the volume, I'm going to do the volume as the length times the width times the height. And so in terms of these variables, we're going to call the length 12 minus 2x, the width 8 minus 2x, and the height x, because when we fold this up, the box will be x tall, and that's what we're trying to figure out as we go along. So we're going to have to do a little manipulation with this. Volume is, let's do the math here, 12 times 8 is 96. Inside I get negative 16, outside I get negative 24. So I think that's negative 40x, and then for the last I get plus 4x squared. All of that's multiplied by x, so I end up with my volume is 96x minus 40x squared plus 8x cubed. Let's take the derivative because we know that's where max and mins occur. So my derivative is 96 minus 80x plus 24x squared. Okay, we quick run to the quadratic formula to get ourselves an answer where a is 24, b is negative 80, and c is 96. I don't have my little handy calculator right here with that program on it, but I'm going to go from memory and say that x is equal to 1.57. You can check my numbers. We're going to get another answer out of this, but when you run this on your calculator, tell me why the other answer doesn't make sense. Okay? So we get some other answer, and we're going to just eliminate that one because it doesn't make any sense, so we're not going to worry about it. But it turns out it's 1.57. I'm sure I remember that number. It's a weird number to remember randomly. Checking to make sure it's reasonable. We do the second derivative, and so we end up with negative 80 minus 48x. And if I do this outright, 48 times 1.5 is about, actually it's plus 48x, isn't it? 48 times 1.5 is about 4872-ish, something like that. 72 minus 80 is negative. Okay, so when x equals 1.57, we are less than 0, which means that we have something that's opening downward, which means we have a max, so we've confirmed that. We always do that second derivative test. Okay, so that's the answer. I have a lot of issues with this particular problem in terms of the whole setup and the arrangement, and if you can come up with a few things about what's wrong with the actual problem, then we'll talk about that tomorrow as well. And so I think we come to there, and we come back to there, and we come back to there, and that's about it. So, as we said at the very beginning, and let's re-emphasize just so you hear it in your own voice, that maximums and minimums occur and we know that we can find critical numbers
when the derivative equals 0.
There you have it. Okay, so that's about all I've got to say for today. Thanks for tuning in, and we're glad to be back up and running and all that sort of jazz. So if you have questions, well, you should ask them tomorrow. We'll see you then. Hope you learned something.